Okay, we've got a bat who's emitting sound waves which bounce off his prey, the insect, back to the bat so he can detect where his prey is. So, part A. What determines pitch in a sound wave? Well, one word answer, frequency. Okay? Pitch is purely determined by frequency, so not amplitude or wavelength or anything like that. Pitch is purely determined by frequency. Okay? Right. Part B. What is the name of a reflected wave? Okay, so when this sound wave from the bat hits the insect, it's reflected back to the bat, like we said. A reflected wave is quite simply called an echo. Okay, simple. Right, next for C, they want you to say what diffraction is caused by. Diffraction is caused by what? Well, the best answer is to say diffraction is caused by the spreading out of a wave. Okay, so let's put that down. Spreading out. Don't say dispersion. Just remember the phrase spreading out. Diffraction is caused by the spreading out of a wave. Okay. Part D. Right, let's do it here. They've told you that the frequency of this of the wave, the sound wave the bat emits, is 25 kilohertz, and the wavelength, represented by lambda, is 0.0136 meters, and we have to calculate the velocity of the sound wave. Right, so this uses an equation involving V, lambda and F. It's the classic wave equation. Well, it's the wave equation. V is F lambda. You should not have to look that up on your formula sheet. It should be in your memory. So memorize it now. V is F lambda. Velocity is frequency times wavelength. So, easy, just stick it in your calculator. Velocity is frequency. Right. Don't dive straight in and put 25. You've got to think about the units. Units of frequency should be in hertz. But they've given us the frequency in kilohertz, so we have to rewrite that in hertz. So 25 kilohertz, kilo is 1,000, so it's 25,000 hertz. Okay? Velocity is frequency times wavelength, which should be in meters, and they've given it to us in meters, so that's fine. You can leave it as 0.0136 meters. What am I doing? You don't write units in equations. Okay, therefore V is, stick that in your calculator, and it turns out to be 340. 340 what though? Well, it's velocity, and if you got your units right, it should be meters per second. Although they actually tell you it's in meters per second in the at the end of the question. Okay. Right. Is that what you'd expect? The velocity of the sound wave that the bat emits is 340 meters per second? Yes, it is, because that's the speed of sound. It's exactly what we'd expect. The speed of a sound wave in air at standard sort of atmospheric temperature and pressure is 340 meters per second. So it's good to, when you get an answer, to ask yourself, is that a sensible answer? And in this case, it's very sensible. Good. Right. E. Excuse me. Describe a longitudinal wave. 2 marks. Right. Well, what is a longitudinal wave? A longitudinal wave is one in which firstly, a sound wave is a longitudinal wave. And okay, I'm just going to dive in straight to the correct answer. Firstly, to get the marks in the exam, just say that a longitudinal wave, the oscillations are parallel to the direction of energy transfer. What am I doing? Parallel to a direction of energy transfer. Okay, that's the best standard exam answer. You can say the oscillations are parallel to the direction of motion, but you still get the marks, but saying energy transfer is the best. Okay, so that's one mark. How do you get the second mark? Well, you just have to remember this. In longitudinal waves, because the oscillations are parallel to the direction of energy transfer or motion, so here's the wave. The oscillations are backwards and forwards in this direction in a sound wave in air. Because the wave is travelling in this direction, so the oscillations are parallel, like this. This creates regions of rarefaction and compression. That means regions where the air molecules have been pulled apart temporarily as they oscillate, and regions where they've been compressed. So that'll get you the second mark. So, longitudinal waves are waves in which the oscillations are parallel to the direction of energy transfer, and this creates regions of rarefaction and compression. Okay, just remember that. Boom, 2 marks, full marks in your exam. Okay, but what actually is a longitudinal wave, and what's a transverse wave? Well, it's that. A longitudinal wave, the oscillations are parallel to the direction of motion or energy transfer. Now that's quite hard to draw, so people tend to represent longitudinal waves like this, which looks more like a transverse wave, I admit, but it's much easier to represent it and draw it like this and try and draw all the compressions and rarefactions. So, what does it actually mean though? What is a longitudinal wave? Well, as I'm speaking to you now through this microphone up here, I'm talking to this microphone, and the sound waves I create an oscillation in my throat with my voice box, and that compresses a region of air like that, a bit like a speaker hitting the air next to it. And that's a region of compression, and that is passed on to the next bit of air. It compresses the next bit and the next bit and so on, and that transfers the energy towards the microphone when you're speaking. So that's a longitudinal wave. And as that compression moves through the air molecules behind it, it doesn't say compress forever, they come apart again, and that's the rarefaction. So the air molecules in one particular region oscillate backwards and forwards, and that's the compressions and the rarefactions. With waves, it's important to realise that the medium which they travel through does not move with the wave. That's very important. The wave moves through the air, but after I stop speaking and the wave's gone, all the air molecules are exactly where they were more or less. I know they're vibrating around. Before I started speaking. So, a transverse wave, which when you draw a wave like this, does actually look much more like that. Good example of a transverse wave is a wave on the sea or a pond. Okay? If the wave is travelling in this direction, say, okay, so this is water waves, and you've got a duck. Oh, that looks exactly like a duck, doesn't it? Yes, nailed it. Okay, if you've got a duck sitting on a pond or on the sea, bigger waves. I don't know what a duck would be doing on the sea. Anyway, okay, this is an adventurous duck on the sea. And the waves are going in that direction. The duck, as the wave goes by, no matter how big the wave, is not pushed in the same direction. All the duck does is move up and down. Okay? And that shows that the medium itself, the water, is not pushed in the same direction as the wave. As that wave goes by, that duck just goes up and down, which shows that in the case of a transverse wave, like a water wave, the oscillations are perpendicular to the direction of travel. So that's the difference between longitudinal and transverse waves. Okay, sound wave, which is longitudinal wave, the oscillations are parallel to the direction of energy transfer. In a transverse wave, the oscillations are perpendicular to the direction of energy transfer. I think that'll do for one question.